Welcome back. This is CSC241, Introduction to Computer Architecture, better known as computer hardware. The day and date is Monday, 13 October 2025. I want to compliment you. Most students did submit a complex logic gate diagram, although some submitted uh, down to the wire. So I did not have a chance to review the diagrams for completeness or to anonymize the results. And when we review them in class, what I want to do is make sure that the names have been changed to protect the innocent, so to speak. So if we have examples that are mostly there or half-baked, that we don't embarrass anybody needlessly. So I'll need to review those and prepare a set of views that exclude the names. And that's what we'll do at the start of class on Wednesday. We'll also begin to take in a review of the Logic Gate E challenge. Now, this was the next assignment before we transitioned into the solution for the module. The solution for the module is more complex. It'll earn you more points towards your final average, and it'll take longer to complete. So the number of assignments and the solution, that's pretty much it. You'll see a 3.3 solution posted by the start of Wednesday. But by the time we start Wednesday, you're going to want to stretch your wings and try on the 3.2 assignment to develop and harden some of um, the concepts and methods that you'll need to be proficient at. So it's a matter of complexity. This is like crawl, walk, run. So um, we do need you to go ahead and finish this between now and then. We'll have a shorter class today, so that'll give you more time to do that. And there's one other person that hasn't submitted a diagram yet. So by 12 noon today, I'm either going to post a 0 for that person, or I'm going to add um, their schematic diagram to their drawing to the batch with everyone else, right? So that's my hope. Um, that's my hope is that we'll have 100% participation in the diagram. As you did in module 2, the diagram that you draw and submit here is the same one that you will use to build out the solution for module 3. Again, for more credit, any questions or comments before we continue?
No, no question.
Um, let's see here. There we go. Um, Let me clear this. Wait a minute. Why is this? I've got the wrong. Can everybody see the screen?
Yeah.
Yeah.
This reference is included in the Module 3 folder called References. And as you may recall, one of the things that I advised at the very beginning of the course is if there is content included in the references folder for a module, you're expected to know it like the back of your hand. Memorize it. Okay. And we stated before that the nans can confuse most students because many nans believe, well, because that not is sitting in front of the and, it's going to flip the output of the and. And ands and ors are kind of opposites. So the prevailing misconception or error in thinking is that A NAND is functionally equivalent to an OR, but that is not the case. And we didn't dive deeper on this earlier to explain, but that's what we're doing now. We want you to memorize this particular reference. It's short but profoundly important. And is always zero unless all inputs are one. And it's best represented by a single standard canonical expression, AB. If we're talking about a simple two-input logic gate with inputs A and B. Does everybody understand that reference?
Yeah.
Now, the NAND is always one. So in that sense, it's like OR, but not quite, unless all inputs are one. When all inputs are true, you have a single case where the output is zero. So what should be true comes out zero. In other words, the single false case, the less common false case, is when, irony of ironies, I've got a true going in, I've got a true going in. In most logic gates, when you put true and true in there, it's going to come out true, but not for a NAND. Okay? With OR, that's what happens. When you put a true and a true into an OR, you get a 1. But if you put just a 1 in either of those, you get a true. The only case, the less common case for OR is always 1, just like NAND, except when all inputs are 0. And the irony there is you put 0, 0, 0, 0, 0 in most logic gates. What you get out is a 0. Okay? So we have a single case for the OR, even though OR likes trues so much that if any true presents, oh, the output's true. So this one's I like to consider to be like the most restrictive basic logic gate. And this one's the most inclusive. Hey, I love everybody kind of logic gate, right? Does everybody understand that reference? Social reference kind of in terms of behavior? Yeah, maybe not. All right. Well, represented by one reverse canonical. So if you have 0 and 0 fed into an OR, even then you still can get a 0 out of an OR if everything is 0, right? But the NOR, right, is always 0. So it's the reverse behavior of OR, just like NAND is the reverse behavior of AND. And you think, okay, this is smelling like AND because everything is 0, unless all the inputs are 1. No, all the inputs are 0. In the case of NOR, if all the inputs are 0, it's supposed to render a 0, but it's inverted or flipped by that not. So it's represented by a standard canonical. It renders a true. It renders a true when the original input for A and the original input for B are false. And again, that kind of defies all logic because if I feed all zeros in there, I usually get a 0. But for a NOR, I get a true. And it's the only true case. And for that reason, it's expressed as a standard canonical A tick B tick. Does everybody follow me so far? Everybody with me?
Yeah.
Okay. So here you have it. Let me just let's look at the last summary. This is a canonical summary we're reviewing. XOR, very special. drawn like an or, except that the back line closest to the inputs is doubled. Does everybody know what I mean by that? It's in your study guide, right? Unless all inputs match. It's always a 1 unless all inputs match. So if we have all zeros or all ones, we have a reverse case. If the inputs match, what comes out is a 0. So whenever you see the word reverse, what we're saying is we're talking about zeros for a final output. Whenever you see standard, we're talking about a true for standard output. And we want to hammer that and go over that in different cases, in more complex cases, starting with the simple, working to the more profoundly compound and complex cases, so that it becomes second nature to you when I say, okay, the deal is we're working with reverse canonicals here. That's the least common output. Everybody should know intuitively, okay, that's a 0 output. That's what we're talking about. The 0 output for an XOR is the case when both inputs are true or both inputs are false. So we say that the XOR is a difference indicator because it's always saying true when we don't have consistent inputs. It's always lit true. The current's always flowing. The light is on when the inputs differ. Any of the inputs differ. It's like a difference indicator. It's like that indicator light on your dashboard that says, yeah, somebody's in the seat, but no, their seatbelt is not fastened. Does everyone understand that reference? We did that in class before. We talked about the seatbelts. Yeah? Yes? No, maybe?
Yeah.
Yeah.
Yes.
Yeah. X nor is always 0 unless all the inputs match. So X nor is like a similarity indicator. If the inputs are all false or the inputs are all true, X nor is saying, yeah, we're good. Everything's off or everything's on. Now, I want you to think about that. I want you to imagine you're in Houston control and you're looking at a screen of a launch pad at the Kennedy Space Center, and they're saying, are we ready for blastoff? And you're looking at your screens. And what do you want to see? You want to see what an XNOR does. You want, yes, nope, everything's off. Hey, it's too rainy. There's lightning. We're not doing this. Everything's off. We're not going there. But what do you want if you're in Kennedy Space Center and you're waiting on authority to launch? What do you want to hear from the Houston Center that controls everything? You're going to want the Houston Center. Does everybody know? Does everybody understand that reference? Has anyone ever seen like Apollo 13 or some of those spaceship launch references where the command center is saying, we're good to all go. Everything's good. You know what I'm saying, don't you?
Yeah.
Profoundly important and yet so simple. I mean, just think of so many different applications that matter. Pre-surgery, pre-flight on the runway with an airline. And here's the jet. Are we ready to go? Are we ready for takeoff? All good? Wait, something's different. Holy bucket, something different. Ladies and gentlemen, this is the captain speaking. We'll need to return to the gate. There's a maintenance indicator that, well, it warrants some quick attention. Before we hurl you 160 miles an hour down the runway so that you become airborne. Big deal. Okay? Big deal. Um, Speaking of big deals, I'm hoping, based on what I shared in the last lesson, that you will also commit to memory this diagram and this view of the XOR implementation view that's in your textbook, because I want you to understand the nuances of a split input. It's the same inputs, ones or zeros, that present in multiple places. And that's a valid use of a split. Now, there are improper uses of splits where, like, you get, and I just want to highlight this, and I see this sometimes in our Module 3 drawings. Can everybody see how the and comes out and it's part of a discrete input, and then this output becomes a part of a separate but different input?
Yeah.
What do you think would happen if we were to join these two wires, splice them together, and we had like an and with an or? I want you to imagine that this is an or down here, and this is an and then the two wires come out, and instead of going into separate but distinctly different inputs, they're fused right here. What would happen with the electrical behavior? What do you think would happen? What
So you're
happens if,
saying,
say again?
so you're saying in the end that or logic gate will have one input?
Let's just say the
Uh,
or isn't even there.
hmm.
This or
I
isn't,
figure it wouldn't work or it would trip out.
yes, correct. Your instincts are sound. Let's say if we had ones and zeros, wouldn't they cancel each other out? It's like, okay, what do I have then? What if you doubled the ones and the current was flowing twice as much? Would that be good to have twice as much current flowing? What do you think?
No. It'll
No,
probably burn.
no. And if you needed to log current for one thing, but then a zero comes along and it shorts it out, is it good to cancel out the one for? No, no. It's Armageddon. So a split here, a join, a split is actually a joined connection between two conductors. We have a conductor here and a conductor here. And I want to tell you that when the conductors are fused or spliced, on the input side, we call that a split. On the output side, we call that a disaster. Okay? Everybody with me? So, why am I sharing this? In the off chance that you're one of the individuals who submitted a beautiful diagram, but you fused your two outputs for two separate, they could be the same, two separate logic gates, and you fused them together into a single, if you joined the fork into a single out, yeah, that's something well, you gotta change. This is your get out of jail free card. You have until 12 noon to make any corrections. Just submit again. If you're one of those that did this kind of thing on the output side, I just wanted to clarify that's not it's not a good thing. Which means I will also add a short but relevant lecture notes reference to the references folder in Module 3 that basically states the same thing in writing, okay? That fused connections with inputs that feed the same one or zero into different logic gates, that's fine. On the input side, that's okay. On the output side, not okay. It's disastrous. Okay? Any questions?
No.
Let's talk casinos. And let's talk switches for just a second. In the world of networking, you've heard of network equipment referred to as a switch. And the word switch is something that applies in different contexts. I wanted to assure you that in the case of network equipment, the context for the term switch is profoundly different. But what is significant about the idea of a switch is that if you combine those switches in an electrical switch that allows you to bridge the connection and complete the circuit versus break the connection and open the circuit, when you arrange those physical switches in series or in parallel, you're creating ands and ors. And that's another profoundly important concept. It's like, okay, when we get into the physical aspects of logic gates and the materials they're made of, it gets to be a really big deal. And what I want to impress upon you here, after we get to the end of this, there are no bounds or few bounds. We just revealed one of them. You don't want to combine the outputs. You have to keep the outputs separate. You can't just splice a connection here where the output is fused into one. But the other thing that we touched on is that the electrical challenges that creates are profound when you short out or short circuit. And this is one of those things that we're going to touch on in much greater detail, I think, in the next, or maybe we do it in the appendix. No, we don't. We're going to touch on this in much more profound detail in module 4. But I do want to finish a thought here. A complete circuit in the real world. So we're kind of transitioning from these software and logical abstractions of the same behavior, ands and ors. In the physical world, a true circuit, a closed circuit, a proper electrical circuit requires a ground. All electrical circuits ultimately ground themselves where? When you hear the word ground for electric circuits, where is that ground? I'm not trying to trip anybody up here. I'm just asking a practical question.
The actual ground.
The actual ground is the answer. Yeah, it's why they call it the ground. So when you search for electrical grounds and then you look at images,
And the black cable is usually the ground.
um, it's all right. So depending on the
Usually
electrical
green, I think, is
application, depending on the electrical application and where it is you're actually working the electrical connections, like in an outlet, electrical grounds are usually represented by the green wire. Black is usually the hot wire. Think black as in what color do people wear at funerals?
you're black,
Black.
Black, right? So which one's going to kill you?
the black one.
The black one,
Oh,
and
Yeah,
then
okay.
and
the
then the
white's
white one is
neutral.
yeah, the white one's considered neutral, but that's for a proper implementation of electrical supply for well, there are different standards. So I want you I want you to know that we don't want to get into physics yet, but we're going to touch on that by the time we finish. And then we're going to go into the flow of electricity quite a bit more in networking in 243 in the spring. It's profoundly important, but electrical grounds, poor or inadequate or non-existent electrical grounds are responsible for approximately 30% of computer hardware and electronic failures. Now, again, we're going to get into we're going to conduct a deeper dive in Module 4, but I want you to know there's an electrical component of every circuit referred to as the ground. And if things are poorly grounded or not grounded, 30% of all computer hardware and electronic failures industry-wide, worldwide, it's because of this. They don't have a proper ground. And that means that when you set up your electric wires in the house, you have an extra wire from the supply panel with a very thick copper wire with a copper stake or a metal stake, and it's driven many feet into the ground. And that's just for the average home or apartment. For large facilities, grounds can take up the size of a small parking lot. And it's very thick wire and it's coiled and it's buried underground. And then there's a huge breaker bar. It's a grounding bar. So it's a very thick, wide, heavy metal bar. And then there's all sorts of grounding connections from supply panels, right? Breaker boxes to that grounding bar. If you want better, if you find a computing environment where things are dying prematurely, aging prematurely, failing prematurely, the number one thing you should check is the electric ground. And once again, we're going to get into some really cool stuff in the next module about that. Any questions about proper grounds for an electric circuit? Yes, no, maybe?
No.
Let's talk casinos. The last segment. Everybody can see this, yeah?
Yeah.
Where are we here? Up there. Now, okay. Remember, we just went through the canonical basics, didn't we? I mean, once you firmly grasp the essentials, how many times with the 4 different combinations of inputs is an and true?
When all is true.
And how often does that happen on a truth table?
Half the time?
So if the A is 1 and the B is false, then and is true?
No.
No. There's only one line or 1 out of 4 where it's true. Does everybody understand what I'm saying about this right here? And I'm just talking about W1 right now. And this right here. Okay? Right? Everybody with
Yeah.
me so far?
Yeah.
I want to call out. Notice the plus sign here. What logic gate or Boolean operator is represented by a plus sign?
Or
Or
It's or, right? So here you see or. So if I have A and B and C and D, 1 out of 4 or 1 out of 4, okay? So if this signal's true, watch what happens. If just one of these is true, then this one is true. Well, what's the output here for OR?
True.
It's true. So what's the output for this OR?
True.
True.
Ah, yep. In terms of sheer probability, and all right, so I'm oversimplifying here, but I'm going to tell you that there's a whole branch of mathematics devoted to statistics, and in particular, this thing called probability. And gamblers, professional gamblers in particular, are fascinated with probability. They know in any deck of cards or in any given gambling scenario, the thing they call the odds. You might have heard of this, where they talk about the odds of a thing being, a win, right? The odds of a win. That's what we're talking about in gambling. It's where the rubber meets the road. Okay. Now, if I build a logic gate, a compound logic, fairly complex logic gate, and I embed Hmm. this kind of solution with physical electronic components, and I embed that chip. I'm going to put it in a chip, a small chip, and I'm going to call this the bait chip. I put this in a one-armed bandit. Does everybody know what a one-armed bandit is?
No.
A one-armed bandit. I'm so glad you said no. It gives me a chance to, yeah, let's do a one-armed bandit here. You ever see these?
Yeah.
They're referred to as one-armed bandits. Slot machines. And you've heard the term, oh, I even spelled that wrong. I'm sorry. I'm so glad that it knew I had happy fingers there. One-armed bandits, right? So people start with less money. They don't go to the $500 a hand poker table or the $1,000 a roll roulette table. They don't start usually casinos need fresh meat. They need fresh blood. They have to recruit new believers. Put another way, nothing breeds the interest in success than a little success, especially after there's a little bit of effort. It's actually a psychological principle known as, and this is important to understand, intermittent reinforcement. Intermittent reinforcement. Now, we're getting into some psychology, and there was a pioneer by the name of B.F. Skinner who worked with rats and reinforcement because he wanted to understand what is it that motivates behavior, reward and punishment. And so B.F. Skinner was a psychologist who did some seminal or groundbreaking or original authentic research. And what B.F. Skinner discovered is that if you give a reward every single time a specific behavior is performed, that's boring. Strangely enough, if you have rats in a cage and every time they press a lever, they get fed, sooner or later they stop because all right, so they know how to get fed, but they're not interested in feeding all the time. So they don't do it all the time. But if you want to create a compulsion, an illness, a driven behavior to continue a thing, when you give a reward only sometimes, when that payoff hits, it's satisfying. I refer you to the gaming world. Is it not true that when you finally defeat the boss at a certain level in a computer game, you just feel good? Is that not a true statement?
That's true.
I mean, that's the nature of it, right? So what are we saying? If you want to hook somebody and you're a casino and you know what? Um, in order to stay in business, you got to keep things going. What you want to do is you want to give the newbies a taste of the rush. So when they pull that handle a few times, oh, there's a payday. I guarantee you, when it comes to newbies in a casino, their job one is to make sure that you get all the free food, all the free liquor, all the free drinks. You check every pleasure sensor mode in your body and in your mind. I mean, they want to make sure that it's a positive experience. And the number one thing they want to ensure of is that you win something before you get bored. So I want you to look at this again. Look at this part of the diagram. Oh, 1 out of 4 times. Now, let's say these first two are all shut down. They're all zeros. I got zeros going into this OR. What's the result here?
False.
No payday. Are you a winner? False. What we want is, are you a winner? True. So what we do is we add some more here. The person who answered a few minutes ago, half the time, that is a correct statement when you have just this. Because a quarter of the time and a quarter of the time, if you have two of these and a quarter of the time this is hitting, well, the other on this side, a quarter of the time this one's hitting. And if either this one or this input is true, then you get a true output here, right? And you're done. Half the time, right here. But let's repeat this. Rinse and repeat. Now we have a third and a fourth. Let's say these are all zeros, but the E is a 1. What is this? Let's say this one is true a quarter of the time. So this is true here. So what happens here? What is that one? It's true. Yeah. So what is this one?
True.
It's true. So if I add this, if I have 3 of these, now 3 out of 4 times, if I had a 3 input OR here, let's say I had a 3 input OR and I had these 3 out of 4 times, I'd get a true. Right? Now that's for 4 pulls. Now relate this back to the one-armed bandit, okay? If I have just this logic gate 1 out of 4 times, it's going to be true. If I have 2 logic gates 2 out of 4 times, it's going to be true. See the numerator here? We have a numerator and a denominator. If we have 3 of those logic gates tied together into a 3 input OR, 3 out of 4 times it's going to be true. But that's for 12 pulls. Does everybody understand? You have 4 rows, 4 rows, and 4 rows. So 3 out of 4 times it's going to be true. What about if I have 16 pulls? Does everybody understand what I mean by that? 16 tries with this structure. What's going to happen? Now, one of the things that mathematicians would tell you is that probability, it's about the odds of a thing being true. And if you flip a coin, yes or no, if you flip a coin, heads or tails. So coin flipping is one of those things that they liken to this mathematical concepts and methods associated with probability. And again, I'm oversimplifying, but 4 out of 4 chance of true. If you flip a coin 16 times, 16 times, you're going to reach a magic state where, according to this structure, you have 8 heads in a row or 8 tails in a row. Again, I'm oversimplifying. Well, that's not the right comparison. The point is that with this logic gate, your odds of hitting a true in 16 rows of truth tables is nearly 100%. Now, that's because in the real world, we flip a coin. When you flip a coin heads or tails, what they'll tell you is that it's 50-50 over time, but you can have short periods of time where you flip a quarter and flip it three times and twice its heads and once its tails. And if you stop right there, you would think, well, two out of three times, that means it's going to be heads two out of three times. Would you bet your house on those odds? Would you bet your house flipping a coin three times and it's heads twice and one's tail? Would you put your life on the line or bet your house on the idea, the simple, the oversimplified, the incredibly ignorant idea that, okay, I'm flipping a quarter and two out of three times it's heads. So you know what? I feel safe enough to bet my house or my life that the next coin flip is going to be heads. How many of you would do that?
No.
No.
Yeah, good answer. Let's say we have somebody that's a winner, 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 chicken dinner. Ooh, I'm hot. I'm winning. What did B.F. Skinner say about that? B.F. Skinner said, okay, now you have something that's been strongly reinforced. Let's look at this one. Everybody see this?
Yeah.
A four input AND. With four inputs, you have 16 rows. Only one is true out of 16 tries. Everybody with me?
Yeah.
Pair it with this one. This is only true one out of what? 16 tries. So if I put the two of these together and I feed them into an OR, 2 out of 16, 2 out of 16 combinations are true. 2 out of 16 for random inputs 1 and 0. Completely random inputs 1 and 0. We look at the truth tables, and I'm talking about odds, and I'm oversimplifying here. It has to do with probability. Fascinating stuff, though. So only twice out of 16 pulls do I get one. Do I hit it? Do I win? Do you understand what's going on here? I sit down for one of these things, and in a short while, we have somebody who's, oh, beginner's luck. Oh, you're hot. What do you think happens eventually? Do you think the house could keep its doors open if you always won and you won more than you paid? What do you think?
No. They'll close.
They would close. Casinos have been around a long time. They're very successful. They make a lot of money. And that's because they're counting on the uninformed new customer. You have just been so informed about how to structure a little bit of electronics so that for one case, oh, you're in the money. And for the other case, not so much. And that is why the house, that's one reason. Well, this is just by extension, the thinking, the concept behind the house is always winning. Okay. Everybody loves to win, but most of the time you're not going to do that. And you have to understand that those games of chance, the odds, always, always, always favor the house. And with the knowledge you have from logic gates in this course, maybe a little light bulb, maybe a circuit has closed, maybe a light has come on in the back of your head where you realize it's not beyond the grasp of casinos to engineer certain games and the equipment for those games so that they can increase or decrease the odds or likelihood of winnings. right? As the Italians would say, capisce, right? Does everybody understand?
Yeah.
Okay. At this point, what we'll do is hit the pause button. We'll review our next round of drawings at the start of class. Thank you for joining us today. Does anyone have any comments, questions, or observations before we close today? I hope I've given all of you something to think about. Have a good day. We'll see you on Wednesday. Bye-bye for now.